The goal of my project was to create a figure 8 using a compound pendulum. First, let's talk about the code. Some things to note before getting into the math part. Rem comments out the code so that it doesn't run. R, we define the radius. We need to define pi. AR is the aspect ratio, which adjusts the screen so that the x and y axes are the same length. And PA is the phase angle, which changes where the pendulum is released in the program. We then define the frequencies. In order to create a figure 8 motion, we need the small part of the pendulum to have twice the frequency of the large pendulum. This means that for every time the pendulum swings forward and back, it will swing side to side twice. This drawing shows a side view of what the pendulum would look like. Now we have a for loop. A is the angle, and step tells it to increment. The for loop using J tells the computer to count to 1,000,000. This helps slow it down so we can see each iteration. A $sign tells the computer to end when Q is pressed. The main part of the program is defining the x and y positions. pset plots these points. Next A increments to the next angle. Now we see the code in action. So the goal was to create a figure 8 using a compound pendulum. So the top part of the pendulum would be attached to a bar like that, and then the second part of the pendulum would hang from that part, with the mass below it. So the entire pendulum would need to swing back and forth once for every time the small pendulum went up and down twice. So the total motion would look like a figure 8. We would want the small pendulum to have twice the frequency of the large pendulum. So to do that, we would start with simple calculations. For a simple pendulum, we know that the period equals 2 pi times the square root of L over G. The frequency would be 1 over the period, or 1 over 2 pi times the square root of G over L. Another way of looking at it is that the small pendulum needs to have half the period as the total pendulum. However, I use the frequencies in the math. So F1 equals 2 times F2. The 1 over 2 pi cancels on each side, and after squaring each side, the G cancels too. You're left with L1 equals L2 over 4. My pendulum was 1 meter in total, so the small pendulum was 25 centimeters. This is a view of the pendulum from above. To get a figure 8, pull the mass back at a small amplitude and shove it to one side before letting go. This initial velocity allows the small part of the pendulum to move side to side. Here are some of my attempts at getting a figure 8. On this try, the bottle was spinning a little, but you can still clearly tell that it's a figure 8. It looks pretty close to the code. Our next program focuses on calculating the energy, so to do that theoretically we use calculus. So energy as a function of time is going to equal the change in energy over the change in time equals some negative because we're losing energy times a constant times the energy. And that constant relates to the amount of radius that we're losing with each swing. So then we would rearrange it, find the integral, use limits, and finally we end up with this formula. And we've seen this formula a lot throughout this year in physics, and what it basically tells us is that the rate of energy loss is proportional to the amount of energy that we have initially. So if we begin with a great amount of energy, we're going to be losing a lot of energy at that moment. So here's part of the code for the program that'll show us the energy. A lot of the variables at the beginning are the same, but we changed the frequency to a formula so that we could add our own data to it. Remember, frequency is going to be 1 over the period, so frequency here is 1 over 2 pi times the square root of L over G. We also needed to add a few other variables like a time component, so we have dt here, and instead of using the angle, we used omega. And then we also added the height so that we could calculate the potential energy. So energy initial is when we pull back the pendulum, and at this point it is not moving, so the only energy that we have is potential energy, so that calculation is pretty easy. Again, we have this component here that slows the program down, This component will allow you to end the program when you hit Q. These two lines of code mark the old x and y positions. We then calculate the new x and y positions. In order to find a velocity, we need to use the distance formula with the change in x and the change in y. We then calculate the potential energy, the kinetic energy, we defined mass above, and then we add them together to find the total energy. This is the formula that we previously found using calculus. These few lines of code are commented out, but when I uncomment them, we'll be able to see the graphs of potential energy, kinetic energy, total energy, and the energy decay. These two lines of code show the animation of the pendulum swinging back and forth from an above view. So it'll go up and back down. We should be able to see the radius getting smaller and smaller. This video shows the radius getting smaller as the pendulum loses energy. And in this clip, you can see my pendulum's amplitude getting smaller as well. Here's a comparison photo of the final products. Now let's look at the energy graphs. Now let's look at the total energy compared to the energy decay we found using calculus. The green line is the total energy and the red line is our calculated energy. Remember, our formula for the energy was energy equals energy initial times e to the negative kt. This is exponential decay. There's clearly a difference between these two lines, so let's take a closer look at the total energy. Looking at our formula for the energy decay, we know that a greater initial energy results in a greater decay. The slope of the light blue line is approximately 0 when there is no kinetic energy, which is the dark blue line, but the slope is at its greatest when there is the most kinetic energy. Therefore, the pendulum loses the most energy at the equilibrium position because it is moving the fastest here. So now that we've created and coded a figure 8 and discussed its energy graphs, here's another pattern that I did for fun. Here, F1 equals 3 and F2 equals 1. This is the program's version. And here is mine. Here's another attempt at a new pattern. The bottle is spinning, which is definitely affecting its motion. As the pendulum keeps going, it is losing energy, so the drawing is getting smaller and smaller each time.